In the last video, I set out to actually talk about regular polygons and tessellations, but the video became so long, too long, as even by the I had it was up to like an hour for regular polygons, so I decided to split it, and then here we are talking about tessellation separately. And tessellation simply means tiling a plane. So if you have seen people placing tiles on a floor, on a wall, or using wallpapers and things like that, you already have an idea what tessellations are about. So let's go ahead and see how this fits into our paradigm of lengths, areas, and volumes. So tessellations is styling the plane. By way of introduction, we see that a tessellation is a pattern made by repeating shapes that cover the plane completely, have no gaps, have no overlaps. So it's more like you're building a house and you have a floor. Like sometimes you have a German floor, and then the finishing would be maybe like some kind of tiles or is it terrazzo and things like that. So the whole idea is that you cover the floor completely, cover the plane completely, and there are no gaps in between the things you use in covering, be it tiles or whatever else you use. And there are no overlaps too. All right. So we have real examples like floor tiles, like I said, brick walls, honeycomb patterns, geometric art, pixel art in games, and so on and so forth. So you can relate to these real life examples. So secondly, let's talk about regular tessellations. So a regular tessellation uses only one type of regular polygon. So in that case, maybe you're only using equilateral triangles. So imagine that you want to have a tessellation. Want to have tessellations of equilateral triangles. So it means you have something like this. Okay. Yeah, this may not be perfect. And then you have something like this again. So where this stops, uh, then maybe you have something like this. Like you just continue like that. Another one. So this may not be looking the best, but that's the kind of idea we're trying to talk about. So you can have different patterns like that. So you can imagine that even tiling requires some mathematics. So a regular tessellation uses only one type of regular polygon, and it has the same arrangement of polygons at every vertex. So same arrangement at every vertex. So the quick question is, which regular polygons can tile the plane by themselves? So if you have a floor, for instance, so you're thinking, are we going to use uh, equilateral triangles all through, or we are going to use squares all through, to arrange? I think the most common patterns you will see will be maybe squares or rectangles, right? I mean, interestingly, a rectangle is not a regular polygon. So maybe we are talking more about like squares. So squares are very commonly used, right, in making tiles. Okay, so let's go ahead and think about angle condition. So there are angle condition for tessellations. So you would know the required angle you need for you to be able to use a kind of regular polygon for tiling. So at each vertex in a tessellation, the angles around that point must add up to 360 degrees. So that's really important. So for a regular tessellation using one regular polygon, each interior angle has got to be the same, right? An integer number k of this must fit. Okay, in fact, I think I want to see if I can show a picture of what tessellation may look like. I'll just check for a random picture online. Okay, good. So you see something like this. Uh, yeah, look at these patterns now. So this is one pattern like that. So you have some different shapes used. So you can see that's another example right there. So you have repetition of beds like that back to back. Then you have this again. Wow, you have a lot of pictures here. So you have all this. Is another one here. So, I mean, you have some one, two, three. So you have some irregular polygons there. Aha, these are more like what we are used to. So you have some big squares and some small squares like that. So you have something like that. This is very common for interlocking tiles. So this also, so something like this. You have this, a lot of them. Okay. You have all these things. These are tessellations. So, okay. Aha, so this is like honeycomb now. So you can see it's like we have some kind of, That's like one, two, three, four. So we have hexagons. Like you have those shapes are looking like hexagons. You have hexagons back to back joined together like that. Okay, so you have different kind. So yeah, you have like equilateral triangles, inverted, face to face, and all that, and the pattern just keeps going like that. So these are very good examples of tessellation. So you can see they have practical applications like this. Okay, so the angle condition is what we're seeing here. For a regular tessellation using one regular polygon, each interior angle is the same, right? An integer number k of this must fit around a point. So if you have k times interior angle must be equal to 360 degrees. That's one thing. So then so interior angle 360 degrees over k for some integer k. So this is the interior angle. So an integer number k of this must fit around a point such that k times the interior angle is 360. So the interior angle you need should be perfectly divisible. It should be a perfect number when you divide 360 by it. So for some integer k, you have the interior angle. So what about testing? So we can test common regular polygons, right? So recall interior angles. For equilateral triangle, the interior angle is 60 degrees. For square, it's 90 degrees. For regular pentagon, it's 108 degrees. For regular hexagon, it's 120 degrees. We saw all of that in the last video, okay? Talking about regular polygons. So for all these angles now, if you want to know that you can use any of these regular polygons to tile a plane surface, to tile a floor or a wall or anything you are thinking of tiling, so you need to test each of them. For instance, for you to know if you are going to use equilateral triangles, so you divide 360 degrees by 60 degrees, which is one interior angle of an equilateral triangle, and the answer is 6. So in this case now, six triangles can meet at a point. So you can actually they are possible tessellates, right? So six triangles are possible tessellates. Then what about square? So if we look at a square, you have 360 degrees divided by 90, and that's 4. So 4 squares can meet at a point. So that means you have they are possible tessellates. Then we have regular hexagons. In this case, you have 360 degrees over 120, and that's 3. So 3 hexagons can meet at a point. So they are possible tessellates. So let's see. Okay, I may need to revisit that. And I think I want to see that honeycomb thing, the picture of the honeycomb right there. Let me see how the hexagons are arranged. Okay. So this is let me see the hexagons for the honeycomb. Yeah, here now. So at one point you see we have three. So at one point like this, we have three hexagons meeting. So you have three hexagons meeting at a point, and that's exactly what we have here because that's 360 degrees over 120. That's 3. So three hexagons meet at a point. So these are possible tessellates. So next, we have regular pentagons. For regular pentagons, 360 degrees divided by 108 degrees is approximately 3.33. So it is not an integer. So it does not tessellate the plane by itself. All right. So for regular heptagons, n equals 7 and above, interior angles are even larger than 128 degrees. So fewer than 3 feet around the point. So they cannot fill 360 degrees without gaps. So you see, very useful regular polygons for tessellation will be equilateral triangles where 6 of them can be at a point. You have squares where 4 of them can be at a point. You have regular hexagons with 3 of them being at a point. Otherwise, other ones are not so easy to use. Okay, so only three regular polygons tessellate the plane by themselves. So you see, these are equilateral triangles, squares, and irregular hexagons, just like I said. So three-sided, four-sided, six-sided, 3, 4, 6. So all other regular polygons like pentagons, heptagons, octagons, etc. cannot form a regular tessellation on their own. So if you want to tile a surface like a floor, a wall, or something like that, so you can use equilateral triangles, squares, and regular hexagons. So let's check example 1. We have showing regular pentagons do not tessellate, right? So interior angle of a regular pentagon, we know that's already 5 minus 2 times, you know that's n minus 2 times 180 degrees. All right, that's sum of their interior angles. Then you divide by 5 to get an angle. So 5 minus 2 times 180, that's 3 times 180 divided by 5, that's 108 degrees. Check how many can meet at a point. You have 360 over 108. So for that you need 3.33. So since this is not an integer, we cannot fit a whole number of pentagons around the point to make 360 degrees. So therefore, regular pentagons do not tessellate the plane by themselves. Okay? So we have another real life tessellations now. So yeah, we can have hexagon tessellation, like honeycombs in beehives look like regular hexagons. That's correct. Efficient packing. I mean, I showed that previously. Efficient packing. Hexagons cover space with minimal wall length for a given area. That's lovely. Then we can have square tessellation. That's one of the most commonly used forms of tessellation. So you have common floor tiles and grids like graph paper. Yeah, like in fact, this thing I've been using. This is a very perfect example of square what is it called now? Okay, did I stop sharing? Okay. Yeah, we're back there. Yeah. So if you have this now, so this is a very so what this system that looks like a graph, this is this is square tessellation. So all these things are squares here. So and they fill the whole surface. So that's a very perfect example of tessellation. So that's why square tiles are commonly used in tiling. So common floor tiles and grids like graph paper, and they are easy to lay and align. They are very easy to lay. Let me see an example here where squares are used. Um, okay, I mean, you can see the usage of squares around all these places. So as even triangles fit into them. So I'm trying to look for a case where we have all squares, so to speak. Okay, I mean, we have big and small squares here. So you have these big squares going like this, and you have the small squares, in the corners like that. Okay, so squares are some of the most common. So easy to lay and align, and they are all at right angles easily. Then you have triangle tessellation. Roof tiles and some art patterns use triangle tessellation. So triangular meshes are used in computer graphics and engineering. Okay. Then we have semi-regular tessellation. So a semi-regular tessellation uses more than one type of regular polygon. So I mean, with regular for if you have regular tessellation, like this one, for instance, this looks regular because all the shapes are about the same. Okay. Um, but of course, something like this will be semi-regular because you're not using the same shape. So once you're not using the same shape, so this one can still pass for regular because you're using cubes all the way. All right. This is not regular by any stretch because we have different shapes like that. So this would be regular because we have that bed shape going all the way, you know. So this is some kind of tiles like that. Okay. So, I mean, I'm talking about the bed one now because even the wall itself is like a tessellation using rectangles in that case. So back here now, a semi-regular tessellation uses more than one type of regular polygon. The arrangement of polygons around each vertex is the same. So examples, you have patterns combining triangles and hexagons, patterns combining squares and octagons. So we've seen a lot of those examples in those pictures we saw. Then students can explore and draw their own semi-regular. So you can draw your own semi-regular tessellation as an enrichment activity, maybe combining squares and whatever. Okay. So, with that now okay, I mean, we have the practice question. That's a fast one. I mean, this is a very good compensation for the last video. Okay. So here, imagine, can a regular polygon with interior angle 120 degrees tessellate the plane by itself? Explain using the angle condition. Of course, 360 divided by 120 is 3. So a regular polygon with interior angle 120 degrees, with 3 can meet at a point. So that's a very good polygon for tessellation. So determine whether regular pentagons can tessellate the plane. We already tried it. The interior angle is 108. And it gives us roughly 3.33. So that's homework. A shape has interior angle 135. Can this regular polygon form a regular tessellation? 360 over 135 is not perfect. So it's not an integer. So the answer is no. And the reason is that 360 divided by 135 does not give an integer value, right? Then question 4, which of the following sets of polygons could form a semi-regular tessellation? Semi-regular. So I mean, we saw maybe squares and equilateral triangles. I think I saw some examples of squares and equilateral triangles previously. Pentagons and hexagons. Pentagons don't form tessellation, so somehow that may not work. Then triangles and octagons might work. I don't know. So Show that regular hexagon tessellates the plane by verifying that three hexagons meet at a point. Of course, in the case of a honeycomb, we have three hexagons meeting at a point there, so they are perfect for tessellation. So a regular polygon has an exterior angle of 72. Determine whether it can tile the plane alone. 360 over 72 is 5, I think. Yes. Yeah, I think so. So uh it can tile the plane alone. Then 70. I mean question 7. Suppose the tessellation uses exactly four congruent regular polygons around the point. What possible interior angles could these polygons have? Four congruent regular polygons. So if you're going to have four, so it's more like, so in that case, just a 360 divided by 4. And that is 90 degrees. Yeah, 90 degrees. So the possible interior angle should be 90 degrees. And that perfectly talks about a square. So for a tessellation, the angles around the point must sum to 360 degrees. Explain why regular pentagons n equals 7 cannot be used in regular tessellation. Because if you divide 360 by the interior angle of a heptagon, you don't get a perfect square. You don't get a perfect you don't get an integer, right? Or you can, if you try 360 over 7, it's not an integer. So and that will be the interior angle of that of a heptagon. So that doesn't work. Then a designer wants to use, oh, is that what yeah, that I mean that may not be the argument, but heptagons don't work. We already know that, right? So a designer wants to use only one type of regular polygon to tile a floor. What shapes are possible and why only this? Of course, we already know equilateral triangle will work, squares will work, and of course, regular hexagons will work. So consider a semi-regular tessellation pattern using squares and regular octagons. Explain how the angle condition is satisfied at each vertex. So, I mean, for squares, right, we have four squares can fit into one place. And for octagon, you can calculate the interior angle, you know. You can calculate the interior angle, and that gives us the right result. You can divide 360 by 8. I think does 360 divide 8 perfectly? 360 divided by 8 is like 180 divided by 4. 90 divided by 2, that's 45 degrees. Yeah. So two of them are perfect like that. Okay. Yeah. So with this, we come to the end of this interesting video about tessellations. That's tiling the plane. And of course, it's plays into the whole idea of regular polygons. Of course, and we can also see. So if you want to tile a floor now, you don't just start tiling. You have to check which one works best. So, and we already know that equilateral triangles, squares and squares, and of course, the last one would be hexagons, right? Can tessellate very well. And of course, some other combinations can work for if you are talking about semi-regular tessellation. Okay. Thank you so much for listening to this interesting video about tessellations, talking about tiling the plane. So going forward, if you're into tiling, you want to do it scientifically by understanding this whole idea that I've told you here. Okay, so don't forget to try your hands on the practice questions. I've, you know, talked about the answers a lot for most of the questions. So you want to try them out to see if you really understand the idea. Okay, till I come your way. Okay, yeah, thank you so much for listening. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much. If you have not subscribed, what are you waiting for? Go ahead and subscribe right away, right? Having done that, you can also become a member of the channel by clicking on join. Okay, so when you click on join, you can become a member of the channel, and that gives you some special privileges. Okay. Um, Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. And don't forget to try your hands on the questions, right? Don't forget to try your hands on the questions so you can really confirm that you understand the whole idea of tiling the plane. To like come your way again, keep doing maths right. Bye.